Welcome to another episode of the Concrete Logic Podcast. And today I have Dr. Aaron Fisher. He is with Ernest Mayer. He's a Vice President of Business Development, and he's on the show today to help us understand fiber rebar. Right, Aaron?
Yeah.
Fiberglass rebar. See, you already corrected me. Good job. Fiberglass rebar. Thank you. Before we get started, though, as I do every episode now, is to remind you how this works. So if you listen to this podcast and you learn something from Aaron today, what I ask you to do is you could do one or three things, or you could do all three things. But the first thing you could do is share the podcast. So share the podcast episode with a colleague in the industry that would get some value out of this. The second thing you could do is go to concretelogicpodcast.com. And in the bottom right-hand corner, there's a little microphone there, icon there. And you just click on that microphone, and it's like sending me a voicemail. And you can either give me ideas for topics or guests, like Aaron here today. Someone suggested I reach out to him and have him on the podcast, so that see how that works. And the third thing, I almost forgot. The third thing, and at the same homepage, concretelogicpodcast.com, in the upper right-hand corner, there's a donate button. You click on that donate button, and it allows you to donate any dollar amount you want. So if you get some value out of this and you're like, hey, I want to throw some money towards the Concrete Logic podcast, that's how you can do it. But it doesn't end there. When you donate to the show, the very next podcast episode that is released, you'll be listed as a producer. And if you want to put that on your LinkedIn profile, on your resume, wherever you want to put it, that is fine. You just put, I was a Concrete Logic podcast producer. And if someone questions that, you just reach out to me and I'll back you up. So that's how you can support the show. And with that, Aaron, let's talk about fiberglass rebar, not just fiber rebar, fiberglass rebar. So, Aaron, I was hoping you could help us out. Tell us what fiberglass rebar is, where it started, and all that good stuff.
Okay. So if you're looking at the codes, it's not going to be called fiberglass rebar. The codes call it glass fiber reinforced polymer, GFRP. It has been an academic curiosity for 50 years because of we know that glass has high tensile strength. We know that concrete does not have high tensile strength. It has great compressive strength, but low tensile strength. And so that's where we started with steel rebar, steel reinforcing bar, great high tensile strength material. Put the two together, you get your nice reinforced concrete. You get a material that's great under compression and great under tension. But there are some drawbacks to steel, as probably most of your audience here knows, between the weight, the corrosion, those kind of challenges. So academics and people who are noodling on things said, all right, why don't we see if we can stick glass bars in there? As you might imagine, glass is a pretty brittle material, so you can't really do just pure glass. Like you can't have a Pyrex reinforcing bar in there. So what they did was they actually made a composite material. They took glass fibers and polymer resins. So the glass fibers provide all the structural strength. The polymer resins hold the glass fibers together. And you move those together, you form them into the shape, and that's actually your reinforcing bar. It's been a thing for 40, 50 years. The ACI committee that actually looks at this material, looks at FRPs, has been around since the early 90s. And hopefully nobody corrects me, because I know actually the ACI president, Dr. Nani, that he was one of the guys who founded this committee. And it's progressed along from academic curiosity to, all right, let's start making some manufacturing. Let's get to the scale. And so now it's a material that's in code at scale, and you can pretty much use it anywhere you're using reinforcing bar. Now, the codes aren't fully like, oh yeah, we can use this every single place that we use steel. But you look globally, it's gotten a lot of adoption. And so we're starting to see a lot of international manufacturers come into the US, and obviously know that the US concrete market, if you could do it here, the engineers are top rate. And so if the engineers here are willing to use it, that's a pretty good bar for folks around the world. So that's a little bit about how long that material's been stewing in the background until it's ready for prime time, which has been a very recent development, actually.
I guess just put in layman, the polymer and the fibers and all, that's basically a glue that kind of keeps it all together. the fibers together, and I assume to make fiberglass rebar, you put in a mold or something, or is it extruded? What's that process look like?
Yep. All right. So I'll get to the two questions. So the glass fibers, like the same, so they're like thin glass fibers that you see, same thing that you use in a fiber optic cable, same kind of thing. You put a bunch of them together and then it becomes like one big mass. You asked how is it pulled together? So the machine is actually called a pultrusion machine. So it both extrudes and pulls at the same time. And so as the fibers are held together and the resin is put there, it cures as it comes out and it comes in a long beam. So if like you wanted a 19-foot run, they just decide, the machine just tells it where to chop. These machines run like 24/7. They unspool it, run it through their machine, run it through the pultrusion machine. It comes out and then they cure it or they cut it and cure it. I will note, so this is welcome to being a guy who actually has a part of my PhD background is actually in polymer resins. That's actually what my advisor did. There's two basic types of resins. There's your thermoplastics and your thermosets. Your thermoplastics, that's like your plastic bottle. If you heat it up, it gets soft. Like it's just a malleable shape. A thermoset is truly like an epoxy resin. So once it sets into that shape, like you can't heat it up and make it more malleable. Your GFRP bars use thermosets. So this is one of the biggest things we always hear is like, oh, can I just heat it up and bend it in the field? No, they have to fabricate it to that shape, that whatever you want in the factory. Now, that being said, any shape you're coming up with, they can do in the factory. These manufacturers have gotten really gifted at it. And it's not some person just standing there being like, I think I got a 90-degree angle. No, this is all machines that are running 24/7. So they plug it in, they take it out of the CAD, they take it off the bar list, and and then the machines just spit out what it is. And that's really how this works.
Got it. So not too dissimilar to how they fabricate rebar now, other than it's a different material. I'm talking about the machines and how they fabricate them and the links and everything. That sounds fairly similar to how rebar is fabricated. Does it come in the same kind of the sizes like steel reinforced rebar?
Yeah. So knowing how to get a product to market is really critical, and understanding what the contractor environment and what the engineers are familiar with. They basically copied everything from steel. So bar sizes, if you want a number 4 bar, that's about a 1/2 inch diameter. They have a 1/2 inch diameter. You want to go up to number 6, that's 6/8 of an inch roughly. They have one of those too. And so exactly how they've done that. And what we've seen with the development actually has been funny enough. The manufacturers have followed a very similar arc to steel manufacturing, 100 plus years ago when we first really got rebar going. The first iteration of rebar was just square rods. And when they started putting that in concrete, they realized like they got the properties they wanted, but the two materials didn't hold together really well. And so the contractors actually had to take the square rods and twist them as they poured the concrete to get more surface area and bond strength, until the manufacturers wised up to this and put in integral deformations, which is, you don't even think about it, but every steel rebar is not smooth doweled. It's integrally deformed. The GFRP manufacturers had to learn that same lesson over, because obviously the first set of bars were just these smooth pieces of polymer resin on the outside. So they were nice. They were dowels. They're great dowels, but they don't have that bond strength you want to concrete. So a lot of the manufacturers were like, let's roughen up the surface kind of deal. That same idea is like twisting the bar in the concrete. They've thrown sand on the surface. That does roughen the surface up. But what they've learned is that the sand bonds well to the concrete, but then delaminates from the bar itself. So what a lot of manufacturers are learning very quickly is they need to go to the integral deformation of bars. And so now, which is a lot of manufacturers are what I in my own way call it a third generation of bars, is the integral deformation. So you feel like it's like a rope that got hardened, like it's like a solid rope. And so that's a big part of when we looked at the manufacturers and looked at stuff and looked at the product, because we are a distributor, we are not the manufacturer, who we were bringing in, what we were bringing in. We looked for a bar that had a lot of these material properties that are equal to or better than steel, because it's really easy to go to a contractor and be like, oh yeah, I'm used to doing number 4s at 8 inches on center. And I go, all right, here's number 4s at 8 inches on center. Like that does us a disservice. Like it's a better bar than that. Like we could probably go to 12 inches on center, or maybe even 16 on center with that same size. But it's easy to go to a contractor. I'm used to going to 8 inches on center. Fine, just keep doing that. And that's been a big part of how we've had to work with the contractor community to get it together is we're like, just do what you've been doing, but look like a Hercules in the field because it's a quarter of the weight. And so they love that.
Why would we want to use GFRP versus steel?
Yeah, this is my favorite. I used to have I have a 4-point plan on this as to why we need to use this.
You sound like a politician, Aaron. I got a 4-point
I
plan.
I actually have a 5-point plan. I don't really need the 5th point. I always joke about this. If I haven't convinced you in the first 4, then I'm not doing my job.
Okay.
But it's the native Washingtonian. If I didn't have a stump speech ready, it's been a blood here. Anyway, what you get, there's 4 big points. The biggest point is tensile strength. The reason we use reinforcing bar is because we need the tensile strength. By switching from steel to GFRP, you go to a material that has 2 to 3 times the tensile strength. That's big. So, all right, now we've gotten that performance question out of the way. So it's stronger. It is lighter. So there's a lot of things that weight plays into. Obviously, most obvious is labor. If you're going to carry a bar from A to B or go up 2 or 3 flights of stairs, if you're carrying 4 times as many bars just because they weigh the same, you're more productive. And there's very little you can do with labor. Like we can't turn labor back into slaves. Like this is not how we're going. The labor is getting more expensive. We're not going to be more productive, but you can have them do the same amount of thing, but accomplish more in that same time. Or conversely, you can think about your cranes on a job site. A big tower crane, how fast that moves limits how much material can get moved. And so now the crane's limited by weight, not by anything else more often than not. And if you can put more material per trip, it's now better. Same thing with hauling and things like that. So lighter has a lot of things like that. And I get into the structural side as well. There's benefits in terms of dead load. If your floors weigh less, your footers now need to carry less weight. Your footings, your pilings now can be thinner. All things like that. Corrosion. This has probably been the biggest point. Ultimately, concrete will last for a very long time. Roman concrete, we're all sitting there trying to figure out every 6 months there's a publication. We figured out the secret to Roman concrete. The secret to Roman concrete is they did not use steel in it. Putting steel in concrete is like putting a time bomb inside your concrete. It's not a matter of if it will fail because of the concrete, because of the steel, because the concrete's going to keep pulling in water. And as the water gets to the steel, the iron elements react and they want to rust. And they start rusting, they expand, they fall. All the issues that we've seen, it's not a question of if it will happen, it's when. And certainly galvanized stainless steel, epoxy coating, that delays that process, but does not stop the process. How do you stop the process? You don't put iron in there to start. You don't put iron, you don't put your steel. And that's where an alternative material like GFRP really has a big win. Sustainability. This is a really big one. Concrete has been, I will say, unfairly the focus of a lot of the sustainability community. And I say this as a true, unadulterated sustainability person. And I think a lot of it's being unfortunately driven by the lumber industry. They say trees are green. The more trees we use, the better. And if we can use lumber in places like mass timber or LVL in place of concrete, they're gunning for the concrete structures. And so they've been arguing that more wood we use, the more sustainable we get. And so they've talked about CO2 emissions. They played fast and loose, and I can go into a lot more detail about that. But in reality, they've focused the environmental and sustainability community on cement and concrete. And I've seen the numbers, they're only about 10% better than us when they choose the numbers. So I'm sure I've listened to a few, Seth, where you've had a few folks on like that explain how to get 10% better concrete. We can do that. But we haven't really talked about steel on a weight basis, while about a ton of concrete gives about 300 to 400 pounds of CO2. A ton of steel gives about a ton of CO2 for like rebar. It's even worse for channel beams and things like that. Well, if you use those two materials together, you're using concrete has its CO2 issues, and then you're using steel, which has even more CO2 issues. That's a problem. But by switching to a material like fiberglass rebar, you can actually reduce the impact of the reinforcing bar by 93%. You can reduce your carbon emissions by that. And so sustainability is a big thing. It's driving a lot of conversation with owners. It's driving a lot of conversation from the government, from state agencies. They want more sustainable. They want lower embodied carbon. And I'm here to present that. And so that's a 4-point plan. I talk through strength. I talk through weight. I talk through longevity and environmental performance, particularly around corrosion. There's a lot more to go there. And then I specifically talked about sustainability. Now, the 5th point, you're always like, all right, this guy's talking about a great product. It's going to cost me more money. It doesn't. And this has been really the game changer recently, where manufacturers have been able to get in that scale up curve. And I'm pointing down because as you scale up, things get cheaper or get lower cost. Cheaper is the wrong word. I know it's not. The product is not decreased in quality. The product's quality has only gotten better, but in increasing production volumes and getting these machines to run 24/7 and do everything you need and automating, they've actually pulled the cost down pretty dramatically. Where we're a distributor, we sell, like you walk in and you're a contractor, all day I'll give you a stick of number 4 for $6, a 20-foot stick. Now, for reference, in the DC market, I know everything's a little bit different in some markets. We only stock domestic steel, but that stained steel bar that we sell is like $10. So you're seeing a difference, like looking at all things being equal, of 40% savings. And when you talk to a contractor and you say, hey, you're going to buy us every day, but I can save you 40% on that. We've had a lot of contractors walk in. They go, why is that? What is this? Explain it to me. We go through exactly that kind of 5-point plan. Well, they're convinced on the money one, the other 4, and they go, let me try it. And then and what we've seen is contractors, once they get in their hands and use it, a lot of the stuff, like I'm underselling it, or they weren't listening as well. But needless to say, they're hooked. They love it and they stick with it. And it's not just us. So you can walk at a Home Depot and Lowe's and buy a GFRP bar there. They put it right next to their steel aisle. If you're looking there, they don't have quite the explanation. Like they have one kind of pop-up panel there to explain what the product is. And certainly people may not be taking full advantage of it or fully understanding what they're doing. But generally, if you're in Home Depot, you're not exactly building high rises. So we're okay there with what they're doing.
Like most of your 4-point plan, there's a 1 or 2 in there I could do without. But so you're saying the tensile strength is 2 to 3 times of steel rebar. It's lighter than steel rebar. It won't corrode like steel rebar. And it sounds like the cost is relatively, it's more, can we use the word of, it's more efficient as far as the way you'd use it? But so if those 4 things, let's say those are all true, all right. So why are we not seeing it more out there? I look at, I don't know, a dozen jobs every week. I go through drawings looking for new work for us. And I can tell you, I haven't seen fiberglass rebar in the drawings yet or specified yet. So what's holding it up?
Great question, Seth. That is, education is probably the biggest thing that's holding up a product like this, because until recently, cost was probably one of the bigger ones. But if you're going to look at construction, particularly commercial construction, specs drive everything. It needs to be in the codes. Engineers need to reference a code. The building code for the local building code has to reference it. And so what has changed recently has been ACI has published a number of codes. There's a lot of international codes. IBS is now adopted. So the specific code that's probably the biggest one, ACI 440.11.22, which was published Labor Day 2022, was like the first code that said, here's how you do commercial design. The 440 committee has been referenced by ACI 318, which is commercial concrete construction, for years at the start of the reinforcing chapter, but nobody pays attention. Like they're not looking at the small font. It said, if you want to do GFRP design, go over to ACI 440. ACI 440 had been reports since the early 2000s. They design guides beginning like 2010s, and it's now a code. So, and then the IBC 2024 has now adopted ACI 440.11.22 as a code by reference. So as codes start refreshing, we're starting to see this. But as you probably know, looking through your specs, engineers like to copy and paste their codes. Like you're looking at specs for details and codes and things like that for stuff we haven't done for 20 years. So it's a lot of education where you bring this up to engineers and you go, I know the pressure you're under from the owner. The owner's asking to get costs down. Okay. There's not much you can do. Like, it's not like we're putting gold plated toilets in and we're like, all right, we're going to substitute our gold for porcelain. Like, there's not a lot of extra money running around in places in a budget. And so we've been able to get into projects at the 11th hour. We basically flip an engineering drawing. We work with the engineer. We show them like things like S Concrete in their software. They just aren't clicking all the buttons. Like, you're not looking for buttons that you didn't know were there. And so you can click a button and say, I want to design my rebar and detailing not to traditional ACI 318, but I want to design it to GFRP, ACI 44011, and use the relevant ASTM codes. And it just does all the calculations for you. And you watch an engineer's like lights go on and go, oh, I thought you were going to make me do like pull out a pen and paper and some slide rules here. And I'm like, no, like, it's in the codes. It's in the software now, that the codes that basically most engineers use, they just aren't clicking. And so we've been able to do a lot of this. And the DOTs are a whole different ball game. I've left them aside. But the DOTs understand the true cost of corrosion. Like, if you're looking at bridges or seawalls or things like, or pavement structures, you deal with the structure. Even down, we were discussing snow beforehand. Even in Richmond, like, if it snows, you're throwing down a lot of salt. I'm sure you've talked a lot about what salt does to concrete and particularly to the rebar. Well, the jurisdictions now are understanding this. They have a rough number of what they do in maintenance. And you look at them and they go, oh. So about 20 years ago, they looked at this product and they said, this could be a big deal. And they actually built some bridges. There's actually a bridge in, welcome to, we're going to play a little geography here, but I'm sorry for anyone who's international or not in the Virginia area. But outside of Roanoke, there's a place called Smith Mountain Lake.
Yep.
There is a bridge over Smith Mountain Lake that was built about 20 years ago with GFRP in it. This was not the third generation of bars. This is much of the early stuff. But you haven't heard about it. Nobody's heard about it because it's still standing. It's working like a bridge. And that's the key thing. But to reinforce this, a lot of these bridges that were built were curiosities. So we've come back and done like core samples. Like, all right, how long is this? What is the quality of the rebar on this bridge? And they actually went and did this about 15 years after. This was Dr. Nani's work, along with a couple other folks. So it's not just him. He's not out there. I don't know if he's the one out there operating the core driller. But they basically looked at these samples and they said, all right, these bridges are 15 years old. They'll go 102 years plus, 100 years plus. And you go, before a major rehab, before a major repair. And that's what these DOTs saw. They've understood this. So Florida's actually been doing it as a DOT for about 10 years. Ohio's been doing it for 5. And like, as they've started to fall like dominoes, because South Carolina, North Carolina, Virginia, I know Maryland's about to drop something. You go up to Maine, you just go down, and like Texas has it. Like, you're like, these states don't agree on anything. Oh, Michigan. Like, these states agree on nothing, but they agree that corrosion costs them too much money in their DOTs. And that has been this big shift and so AASHTO has bridge design guides and things like this as well to drive that side of the community. But again, it's an education piece. Like, I joke with engineers all the time, or they'll tell me like, look, if you're driving on a bridge in Maryland and a bomb happened to hit it, the bridge would still be standing after the bomb. Now, shrapnel, I'm not going to go on what the shrapnel might do to you, but the bridge will still stand. And they go, we have over-engineered bridges for 40 years, but we haven't touched the spec in 40 years. Like, it is, and that's been the challenge, is that we're trying to update specs, get new materials in. The most common, when I go to talk to someone at a DOT or a state agency, they're like, why would anybody want to do this? Like, I need a project in front of me. But I go to an engineer and they go, I'm not going to spend my time engineering this unless it's in the codes already. And then the contractor goes, we're not going to propose this unless the engineer and the regulator bless this. And what's funny is you get all three of them in the same room and they go, nobody has an actual objection to this material. And that's what we're starting to see a shift, is there's people who are able to pull those three groups together and move the needle. And that's where we're starting to see a lot of projects move very quickly that are very public. You go down it and it's stunning how quickly this is done. Virginia VDOT, which does not have a standard, has actually snuck it into the harbor tunnel projects under design build. So design build, obviously, you're not exactly having to follow the state specs, you have a little bit more latitude because the engineer and the contractor are working so closely together. They are able to make the case by themselves without the regulator, but to the level of confidence that they can take the engineering level of confidence and they can actually do that and they can actually incorporate it into those structures. So we see FRP down there, and that's what we're seeing is it's just sneaking in a lot of places. And now we're seeing that people are like, oh yeah, we need to formalize this. And so that's where a lot of the AASHTO design guide, the ACI has come along, TMS, the Masonry Society has come along, and everybody's putting these codes together and they're starting to make sense. But the field is rapidly changing in front of us, which is both good and scary. But needless to say, I think the biggest thing I can get to your audience is if you designed a bridge with steel, you can pretty much up into the 11th hour convert that bridge over to GFRP. And it would function the same way. Cost and on material basis is like roughly going to be pretty close. So on a commercial job, you're buying much more direct from a mill. Like there's a lot less markup coming through. You're pretty close on cost, but what you're really going to save on is maintenance and longevity. You're going to have a bridge that lasts 100 years, doesn't need nearly the same maintenance, and is gravy on top. As I mentioned, it's a sustainable material. So for jurisdictions that are under that kind of decree, it's going green without spending more green.
Oh, do you have that trademarked?
I say a lot of things.
Going green without spending a lot of green?
Yeah,
you should trademark that, Aaron.
I'll try to. I'm a reformed sustainability guy. More times I have to argue with people in the sustainability community about what's practical.
Right.
And I'm like, because I don't care if we have something that's purely like the greatest thing since sliced bread, but if it costs too much money and no one's going to do it. And so that's kind of it. So going green without spending more green. I guess I'll trademark. All right, full trademark there. I'll stop arguing that I don't have the trademark and just take it.
Just take it. Yeah. So, but when you're doing these conversions and you're getting people on board to use GFRP, you got to explain to them the limitations of it too, right? There's got to be some limitations that you got to be upfront with them to tell them, hey, I don't want you to be surprised when you run across this particular condition or this particular building element. GFRP is not the thing. Is there anything like that you let engineers and designers know ahead of time?
So certainly there are certain things, and I think it has to do with where the code is now. So engineers like that. Code is a safe space for engineers. Mm-hmm. And what does the code say now is you can't design in high seismic, D, E, and F seismic. Okay, but what can I tell you is Japan has been doing this since the 90s. Everything in Japan is high seismic. So what the challenge is actually, it's a bigger discussion in the seismic community where, and I'm sorry, I'm going to do a little bit of a visual here, but for anyone who's watching, I'm showing like when a building goes through an earthquake, it moves. And generally what we rely on is the steel kind of dampens that motion back and forth like that. Internationally, that is not how seismic reinforcement is done. They actually have the whole building rock and then it slows down as one single piece. In that kind of design, because the bond strength between the bar and the concrete is so much higher, it actually holds together. Now you're not trying to figure out how damaged your bar and your concrete is to each other as you would when it happens like this. That's a bigger discussion. Like I'm trying to, but because the rest of the international community was already pushing this way before GFRP came onto the scenes, we're starting to see the seismic codes reflect that. And that's leading to some changes. But if you're using ACI 44011, I have to tell you, you can't do it with ACI 440. But we know how to. The engineering is there. What else I can tell you, if you're a structural precaster, certainly this is an area that people are looking at, but ACI 440 says this code is not talking about structural precasting, particularly around pre-stressing. It does not talk about pre-stressing. Why? The material behaves slightly differently. So if you were to bend steel and bend it back, it gets back to where it is, but it doesn't quite come back to where it is. And so in a stress strain curve, it keeps moving. It has an effect that you've damaged it, like it remembers the damage. GFRP is actually different. Until it breaks, it goes right back to where it is. So the motion is, so there's not a question of, hey, how many times is it bent? I don't care. Either it's broken or it's not. That's the binary condition we get to. That's truly what a brittle material is. Like everyone thinks of like your grandma's vase as brittle. It's truly brittle. Like if you drop it, we know exactly what's going to happen to your grandma's vase. It's not, you're going to have a really upset grandma. If you take a bar and drop a bar from the same height down to the ground, it stays together. Like it's brittle, but the failure point is so far beyond where you expect because of what the resin is imparting. It's imparting those properties to that bar. But the way the code takes care of that is that they take you much further away from that failure point. And so why GFRP, while it might be like 180 KSI, the code only lets you 150 to 180. You can only use about a third of that value if you're stressing it. So, all right, that takes you down to like 50 to 60 KSI. That's equivalent to where you can take your steel, like grade 60, you can stress it to like 80% because it yields. You're in the same ballpark, but that's where a material like carbon fiber reinforced polymer actually comes in, CFRP. It is much more expensive. This is not but performance-wise, its tensile strength is like 350 plus. So a third of that, you're over 100 KSI. Like you can really bend it. You can really stress it, and you're still nowhere near the failure point. What else could you get into? Let's see, other applications that certainly, those are probably the two biggest ones. As I mentioned at the outset, people do always get worked up that you can't bend it. But I can tell you as a guy who works with out in the field with folks, like we stock common bends. So you need an elbow, you need a stirrup. Like if we know what's coming, we can do that. Obviously, everything in the factory, the lead time is to get to site for like a big truckload is like 2 weeks. If you need like something immediately, as I mentioned, these machines run 24/7. They just pull it in and they can airship it because it weighs nothing. So like if you forgot like an exact piece, there's nothing else you can do there. You can do that. But that being said, the way the codes are written, you can lap in with steel. Like they are very conservative and detrimental to GFRP in favor of steel. You could lap in with steel. Say you needed some bend and you couldn't get it. And you're like, I could walk over to Home Depot and get it. All right, great. Bend it in with steel. But that being said, you get to like a residential corner and you're used to having those corners there. You're like, all right, that's great. It's actually stronger to do a 45-degree lap splice. Why? As you might imagine, when you bend glass, it tends to start breaking the glass. So the fiber starts to damage. And so a straight glass bar is actually stronger in the directions that you're interested in. And then once the concrete's in place, the bond is actually not between from the bar to the bend to the other bar. It's from the bar to the concrete to the other bar. And so the concrete is really the glue. You're just trying to hold it for placement. And it requires a lot of conversations. And when I get in front of a contractor who's really understanding this, like there's a lot we can do. Like what we do pretty regularly is a contractor says, oh, I'm used to using number 4s or number 5s in the thing. I go, downsize. That number 5 grade beam, all those bars in the grade, you can use number 4. I have details that show that. I have a Ryan Holmes detail. I mean, NVR Homes, they are, look, I joke all the time, but to their credit, they make affordable housing, but they are the kind of people that they would sell their grandmother for a nickel. Like they are very interested. They understand their costs and they're doing everything they can to drive it down. I've got it in front of them. I've got their drawing flipped. And that's the kind of thing where it's like, and they're looking and they go, all right, I know exactly what it is. We'll compare bar to bar. If you guys are cheaper on a job, we'll take you because you meet code. If steel's cheaper on a job, we'll take you. And that's really where it is with a lot of this stuff is that, but I'm pricing against number 5 steel. So I have my $6 bar and I'm trying to compete with someone's number 5 steel bar. I'm at a really good advantage there. And that's how we get a lot of this cost advantages is you're looking at a big structure, number 8s, number 7s. I can take that number and get number 6s. That's a big downsizing bars has, while it helps with material, it also helps with placement. It helps with confinement, congestion, those kind of things. And these are the kind of things you don't think about. And it's really tough to get someone to understand it. But once we get people using it, there's a lot of tips and tricks we can give somebody that makes them, they just, whatever the hook is we get into you, we can, and then we give you the rest of the store with it. And they really are sold.
Yeah, I think that's a perfect spot for us to stop today, Aaron. If folks want to reach out to you and learn more about GFRP and maybe say, hey, I got this job, can you flip it from rebar, steel rebar to GFRP? What's the best way of them getting a hold of you?
Best way to get in touch with me, email. My My name is Aaron Fisher. My email, afisher, AFISHER. There's no C in case anyone's wondering, at emco, EMCO block.com. I guess I'll put my phone number if somebody wants to call me, 202-510-5545. If you want to give me a ring, I generally answer my work phone at all odds hours. So I'm happy to be a resource. I'm happy to connect you with folks. I'm not the only person who knows this, but certainly I spent my time to get this up to speed, and we're really convinced. We've convinced a lot of folks in the DC area. So big shout out to Reliable. Any job they can get their hands on, they're giving to us. And they're like, just, you guys save money. Like, we like it. We save money. We save money on material. We save money on labor. And then ultimately, we're winning more jobs because it's just cost effective. And that's really the thing. If you're struggling on cost, you're not winning some bids, give us a call. Hopefully we got a solution for you.
It's cool technology and definitely something for folks to look into. All right, Aaron, I appreciate you coming on the show today. Folks, until next time, let's keep it concrete.